Question 1 says, two identical billiard balls collide with each other as illustrated in the diagram below. Now, when we look at this diagram, we have a before situation, a before collision, and I have two identical. To say these objects are identical, it means that they both have the same mass. Let's say I have M1 to be M here. We also have M1 to be M here. Right? I can give them the variable M, these two masses, M1 and M2. Sorry, this is here M2 because they're exactly the same. Right? They're identical. That's what it means. Now we can see that the black 8 ball actually moves to the right with 4 meters per second, and the 5 orange ball doesn't have a velocity. We don't know what its velocity is. They've just written V2 initial, right? It could be going in that direction, it could going in that direction. We are not told. We don't know. But we know that it is moving because they say that they collide. So it could be moving in this direction with a small velocity than this one. That means this one will catch up and and collide with it. For example, if this moves with 1 meters per second to this direction, this will be able to catch up and collide with it. Then if it moves towards this object, definitely it will also collide because we are told that they collide. It is also possible that it is not moving. We don't know because we're not told. Because if it's not moving, this object will be able to collide with it. It will find it stationary and collide with it. So those are the possibilities here. They further say to us that, well, obviously we can see after collision that the two balls move, both of them move to the right with velocities 2 and 4 meters per second respectively. Now they further say here that the net external force acting on the balls is 0. A very, very important statement, because that statement actually says that this system here, because actually we have a system here, this system here before and after collision. Remember, it's a system because we have a group of objects interacting with each other. Is actually an isolated or a closed system. And that is important because it tells us that our linear momentum would be conserved if that's the case. The other part to it is that they say to us, ignore the rotational effects of the balls. We briefly talked about this to say these balls actually will rotate as they move. In fact, you can see from after collision that the 8 is actually sitting diagonally to say that this object is rotating. Look at that 5. It has actually moved, and is now sitting sort of horizontally to say this ball has rotated. It is actually rotated, and now it has a different orientation. Now, these effects are ignored because when this rotational motion takes place of these balls, we have things called angular momentum, angular speed, or velocity, and we have also a concept called moment of inertia. All those things at high school level, we don't study them. So what they're saying is that do not worry about including those here, right? So that this question it becomes much more simplified and fits well into our syllabus. What I have done here so far is what we call problem interpretation, given by the symbol I. To conclude my problem interpretation, I would choose also direction as part of my interpretation to say take the right as positive. Very important to choose direction when you deal with problems of this form, because these vectors here, we see vectors that are drawn as velocities. Before I attempt to answer questions, I'll sort of pause a little bit and ask myself, what part of physics does this problem fall under? And I think this would be something that has got to do with the law of conservation of linear momentum. And because already we studied linear collisions, I would say here that we can also expect to use the knowledge of elastic and inelastic collisions. We call that classification of the problem. I'm classifying this problem as a problem of linear momentum, the conservation of linear momentum, and the understanding of types of collisions, elastic and inelastic collisions. Then the third thing that I'll do is then go and answer the question, the A there. The first question then says to us, state the principle of conservation of momentum in words. They want us to state it in words, and this is for 2 marks. So 2.1, I'll jump into it and just answer the question. We know that the conservation of momentum states that in a closed system, the total linear momentum before a collision is the same as the total linear momentum after the collision. And this would be marked out of 2 marks. And the last thing that I will do is that I'll check my answer to see if everything is correct. There's no spelling errors here and my grammar is correct. So literally I'll check to say what I've written makes sense. We're saying here in a closed system, the total linear momentum before a collision is the same as the total linear momentum after collision. So it seems like everything is okay. When I do that, when I check my answer to see if everything is okay, we call that navigation. I'm navigating my problem. And at the end of the day, I was following the rules that are called the I, C, A, and N rules. This is the problem solving strategy that I'm using to solve this problem. This strategy says to me that I can solve any problem if I follow it. Now, using the same technique, I'll then go back to answer the second question. So it means I'm circling back from navigation to answer again. So I'm going to answer now 1.2. That says to us, calculate the speed V2 initial, this one here, before collision. So we want to know what was the speed of the orange 5 ball before collision. And speed would mean that we only want the magnitude of the velocity, not the direction. However, in our equations, we will put direction, but the final answer will be reported without direction. Because we said that this is a problem that involves the law of conservation of momentum, because there's 2 objects interacting with each other, there's a system, and also that it's a closed system because they said there are no net external forces. It means the momentum should be conserved, as we have answered here in question 1. In fact, question 1 was giving us a hint that we are going to use the law of conservation of momentum. So this means here I'm going to use my equation to say m1 v1 initial plus m2 v2 initial, which is the total momentum before collision. It has to be constant. It has to be the same as m1 v1 initial, the momentum of the first object final, not initial, plus m2 v2 final, the momentum of the second object final. So this is the total linear momentum after collision. We're saying the 2 momenta should be the same before and after collision. Because the system is isolated, it's a closed system, there are no net external forces acting in the system. Now we have to realize that this is a special case problem where our masses are in proportion. Remember, in our lesson 6, we discussed this to say when the masses are in proportion, then our velocities will be independent of the mass. Right, I'm going to do it in full here just to help you practice this, and then later on we'll stop doing it in full. This means here I'm going to substitute the mass as m, because we can see that these masses are in proportion. Right, they have a ratio of 1:1. They are identical in this case, we have the same mass. So I'll say m1, and I'm going to write this as v1 initial, and I'm going to have this as m, and here I'm going to have v2 initial is equals to, here I also have a m v1 final, plus here I'm going to have m, and we're going to have v2 final. Now I can divide this whole equation by m here and m here and m and also m, so that the m and the m cancels, the m and the m cancels, all these m's will cancel. Hence we're saying that the velocities of these objects are independent of the mass. We don't need the mass for us to be able to calculate the velocity. Now our equation has reduced to something that doesn't have the mass because they've cancelled. Now here I can substitute so that I know my initial velocity was 4, and I'm looking for the initial velocity of the second object, and we know that the final velocity of the first object was 2, and this one was 4 as well. Right, I'm just substituting now these numbers, right, and they're all positive because they're going to the right, and I chose right as positive. Now at this stage, these problems becomes very, 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 very boring, because we can all see that our speed would be given by a 2 meters per second. Remember, here I'm going to have a 6, and I'm going to have 6 minus 4 because I'm taking the 4 to the other side, and that should give me 2 meters per second. I'm not going to write the direction because the question was actually asking me to calculate the speed, so only the magnitude. And this question, it is out of 4 marks, so that means we are going to get a mark for writing the correct formula, for doing the correct substitution, and the fact that also your mass was able to cancel, this is part of the substitution, and the 1 mark for the final answer. Before we go any further, perhaps the last thing that we'll do is to go back and navigate this answer, because the type of question that we're dealing with here is a calculation problem. So when you look at your answer, when you navigate your answer, meaning, remember, I've answered this problem, I'm now navigating, right? I check if there's any errors, if I've written everything correct. The first thing that you have to check is that did you calculate the correct thing, right? Yes, I did, because we were looking for V2 initial, right? And I've written my number and the SI unit, because velocity has the speed has the magnitude and the SI unit, so everything looks good. And this answer as well is a reasonable answer, looking at the fact that I'm already having these nice small velocities. If I were to get an answer of 100 here, or maybe an answer of 50 here, it will be alarming, because these objects are already moving at relatively small velocities. I can't suddenly have a big velocity, right? So this would make sense. It's a very reasonable answer, right? So that is part of navigation when we navigate the answer. Now we are going to circle back to A to answer the next part of the question. But this question actually gives us more information, because they then say to us here that the mass of the number 8 black ball, right? So the mass of this ball, they are now saying that it is given by 0.17. So we are saying here that this mass that we called m, it is now 1.7 kilogram. By default, it also means the mass of the orange 8 ball should also be 0.17 kilogram. The reason being is because these two balls are identical, meaning they're exactly the same. They only vary with color. Right? So it means here they've given us more information. That means we were reinterpreting the problem. We actually are not at A, we are reinterpreting the problem. Right? So we are yet to again, I'll still classify this as conservation of momentum. Maybe they'll ask me further calculations on the conservation of momentum, or maybe collisions, because already we answered the conservation of momentum. So now we can answer the question. We are at the point where we answer. 1.3 says, is this collision elastic or inelastic? And very interesting, this question is worth 7 marks. Obviously, this means we're going to run a calculation for us to get 7 marks. Remember the definitions of elastic and inelastic collisions. So this means for us to answer this question, we have to assess the total kinetic energy of the system before and after collision and compare the total kinetic energy before and after. If our total kinetic energy is the same before and after collision, we then say this collision will be elastic. If it is not the same, we say it is inelastic. And we are going to do exactly that. It's a very simple question to actually come across. For me, this, are the type of 7 marks that I would say are easy to get. Because what we do here is that we are going to look at the total kinetic energy of the system before collision, initial total kinetic energy, which is given by half m1 v1 initial squared plus half m2 v2 initial squared. And I'm just going to substitute here to say I have my mass given by 0.17 now, we are told, and we are multiplying this by the initial velocity of 4 for the first object squared, 1 over 2, 0.17, and we are multiplying this by a velocity of 2. Remember, we found this velocity to be 2 in the previous question. And from here, this question becomes really, really, really boring, because you just press a calculator to then calculate your final answer. And I get an energy of 1.7 joules. So this means that my initial kinetic energy is given by 1.7 joules. And I'll do the same by finding the total kinetic energy after the collision, which will be given by half m1 v1 final squared plus 1 over 2 m2 v2 final squared. And again, this becomes a substitution problem. Another thing that maybe we may like to do is that we can notice that these two masses are the same, meaning I can write this equation as 1 over 2 m v1 final squared plus 1 over 2 m v2 final squared, so that I then take the m and a half as a common factor, because m and a half appears in both these two terms, so that now I have v1 final squared plus v2 final squared. And at this stage, I can then substitute to say I have 1 over 2 0.17. This, I'm just doing this so that when I punch my calculator, I don't have to punch this twice. I can only punch this once. Then here I'm going to have my initial velocity to be, my final velocity of the first object to be 2 squared plus, now this is not velocity, is speed, because on the formula of kinetic energy we only work with speed, and the final speed will be 4 meters per second. I'm going to take the 4 meters per second squared. Let's double check. Yes, that is 4, 2 and a 4. Now from here we're going to simply use a calculator to say I have 1 over 2 multiplied by 0.17, and we have a 2 squared plus a 4 squared. It becomes easier to punch this on a calculator than actually to punch that, but I mean it's a matter of preference. It is up to you. I get the same number here of 1.7 joules as well. So that means my total kinetic energy after the collision is actually the same as the total kinetic energy before the collision. So here I'm going to say that I'm going to answer my question to say, since the total kinetic energy before the collision is exactly the same as the total kinetic energy after the collision and is given by 1.7 joules, thus the collision must be elastic. The collision is elastic. Then we have answered our question. Now let's see how the 7 marks comes about. Where will it come from? And this is very important because you need to know where the 7 marks comes from. You don't want to lose marks because you didn't write stuff. So the first mark would come from writing your formula for the initial total kinetic energy. The other mark will come from correct substitution, and the other mark will come from writing the final answer of the total kinetic energy initial. This will be marked in the same way: 1 mark for the formula, 1 mark for the correct substitution. Yes, I know I took some time doing this, but I was just showing a technique. In an exam, you can move from here to here. You can move from this formula to this formula directly. And the other mark will come from actually writing or finding the correct answer for your kinetic energy there. Now, the last mark will come from actually answering the question to say this collision is elastic, because we know that the total kinetic energy is conserved. It is the same in this system. Now, let us navigate this question quickly. In fact, I didn't want to navigate this problem. I didn't want to do the end rule here because we answered the question, because already it confirms to me that it is correct. I have a lot of confidence that is correct because, when you get answers like this, then they tell you that you are in the right path because our kinetic energy is the same. There's nothing much that I can do here. If they were different, I would look into things to say what could make them to be different. But in this case, it's a straightforward question. I think it looks correct. And, it is not a big number because we are not dealing with big velocities as well, or speeds. We have reasonable speeds of 2 and 4.